Welcome to Full Spectrum Science Shorts. I'm your host, Ron Hipschman. This is the season when the Exploratorium constructs its graveyard of dead science ideas, and I've resurrected, if you will, one of those dead ideas. The steady state theory. Our story begins with an astronomer I'll bet you've heard of. Well, at least you've heard of the telescope that was named after him, the Hubble Space Telescope. Edwin Hubble played a vital role in our understanding the size and evolution of our universe. Hubble arrived at the Mount Wilson Observatory in 1919 after serving in the Army in World War I. Mount Wilson is just north of Pasadena, California, at 5,700 feet above sea level. There, Hubble used the newly completed 100-inch Hooker telescope to continue his research of nebulae. This was the largest telescope in the world at the time. Previous to arriving at Mount Wilson, Hubble had written his PhD dissertation titled Photographic Investigations of Faint Nebulae, and he was going to continue his research at Mount Wilson. Nebula is the Latin word for cloud, and indeed, nebulae are giant clouds of gas and dust. Some of these clouds, like the Orion Nebula you see here, or the Cepheid Nebula in the constellation of Sagittarius, are the birthplaces of stars, giant nurseries where gravitationally collapsing clouds are creating new stars and solar systems. Other nebulae, like the Ring Nebula in the constellation Lyra the Harp, are displays of the end of a star's life. A star about the size of our Sun, or maybe slightly larger, once it uses the bulk of its hydrogen fuel, collapses and simultaneously expels a shell of gas, exposing a hot white dwarf remnant, which illuminates the gas, causing it to glow. This nebula was also the result of a star's ending its life, but in a much more violent fashion. Large stars at the end of their lives don't gently collapse and puff off their outer layers like the star in the previous slide of the Ring Nebula. They collapse and explode in a supernova. A star in the constellation of Taurus, the Bull, exploded in 1054 AD and became bright enough to be seen in broad daylight, creating the Crab Nebula. That star is a pulsar, spinning 30 times a second. Other fuzzy patches of light in the sky had interesting spiral shapes. These were called spiral nebulae. This photo was taken by that 100-inch Hooker telescope on Mount Wilson. Hubble's namesake, this Hubble Space Telescope, in orbit around the Earth, somewhat improves on the original photo. These spiral nebulae came in a variety of shapes and sizes, like this rather open spiral. Sometimes they seem to have a straight bar running through the center, with spiral arms trailing from the ends of the bar. Others showed no arms at all and were elliptical blobs, while still others were irregular patches in the sky. This is the Large Magellanic Cloud, visible only in the southern hemisphere. Hubble came up with a classification system now known as the Hubble tuning fork because of the shape of his diagram. The ellipticals were numbered from E0 to E7 depending on how elliptical they were. The spirals and barred spirals were labeled SA, SB, and SC, or SBA, SBB, and SBC, depending on how open they appeared. Irregulars were just, well, irregulars. We need to divert and go off on an important little side story. When you look out in the sky, you may notice that not all stars shine with a constant brightness. Some stars change their intensity in regular ways over a period of hours or days. These were called variable stars. Some are double star systems that eclipse each other from our point of view in the solar system. We don't see the individual stars, but when they move in front of each other, the combined brightness changes. Other variables are single stars that grow and shrink, changing their brightness as they do. If you chart their brightness over time, you may get a graph that looks something like this. This particular type of variable star is one of those that changes its brightness intrinsically by repeatedly getting bigger and smaller, growing in brightness and shrinking and dimming in a cyclic fashion. The first one was discovered in the constellation Cepheus the King and is the fourth brightest star in that constellation. This type of variable star is therefore called a Cepheid variable. Why is this important to our story? In 1912, Henrietta Leavitt, an astronomer at the Harvard College Observatory, made a remarkable discovery. She had cataloged almost 1,800 variable stars in the Large Magellanic Cloud. Of those 1,800, 25 were Cepheid variables. Since all were in the same small galaxy, she knew that they were all at about the same distance. She discovered that the longer they took to get bright, that the brighter the star actually was. If you know how bright a star actually is, its luminosity, and you see how bright it looks to you in the sky, you can figure out its distance. Think of it this way. You know how bright headlights really are. If you see a headlight and it looks dim, you know it's far away. Likewise, knowing how bright a Cepheid really is gives you a measuring stick to figure out how far away it really is by how bright it looks to you. Cepheid variables will play an important part in our story of the universe. If you go outside and look up in a dark sky away from city lights, you'll notice the dim trail of the Milky Way. From our point of view inside the Milky Way, it looks like we're near the center of a flattened disk of stars. It surrounds us completely. Here, in this horizon-to-horizon fish-eye view, you see the Milky Way as it rises over the Paranal Observatory high in the Atacama Desert in Chile. If we could view it from the outside, it might look like this, a flattened disk of stars, with us in or near the center, surrounded by the stars and nebulae that made up our entire universe. Hubble observed the Andromeda Nebula and photographed it in great detail. This is a modern photo of Andromeda. Hubble's photos had far less detail and were in black and white, as you'll see. On the night of October 6, 1923, Hubble took a photographic plate of the Andromeda Nebula using the Hooker 100-inch telescope at the Mount Wilson Observatory. Here he is guiding the telescope for the long exposure this required. Here's the plate he took that night, with identification number H335H, meaning Hooker, plate 335, by Hubble. Of course, it's seen here as a negative. Let me reverse it for you so it looks a little more familiar. Note that aside from labeling the date on this plate, he also labeled stars with an N. These were stars that did not appear in previous plates. They were new stars, or novas, actually stars ending their lives in spectacular fashion. One of the stars in the upper right of the plate that he labeled as a nova at first turned out to be one of those Cepheid variable stars. He crossed out the N and relabeled it. You can tell he was excited by the exclamation mark after the var designation. This was the discovery of the first Cepheid variable star in the Andromeda Nebula. Why the excitement? If he could measure the period of the Cepheid variable star, he would know how bright it really was, and by comparing that to the brightness it appeared to him, he was able to determine that the Andromeda Nebula was really the Andromeda Galaxy, another complete island universe similar to the Milky Way. Hubble calculated that the Andromeda Galaxy was over 800,000 light-years away. It's actually 2.3 million light-years distant. That also meant that all the other spiral nebulae were also galaxies. Can you imagine how Hubble felt making that discovery? The universe became a lot bigger on that day. In addition to variable stars, Hubble also looked at the spectra of galaxies. Dark lines in the spectrum are absorbed by various chemical elements. The dark lines occur at very distinct colors or wavelengths. Hubble noticed that the lines he saw in the spectra of galaxies were almost always shifted toward the red. This was due to the Doppler effect and is called a redshift. It indicated that the galaxies were moving. Here is an animation of the Doppler effect. Circular waves are emitted from a moving source marked by the yellow arrow. Behind the source, the waves are stretched out and spaced wider, or redshifted. Ahead of the source, the waves are compressed and closer together, or blue-shifted, all because of the motion of the source. The faster the source moves, the bigger the red or blue shift. Hubble looked out and measured the spectra of many galaxies. By looking at the shifts of their spectral lines, he was able to learn how fast they were moving. Stunningly, virtually all the galaxies were moving away from us. Using Cepheid variables, he could measure the distances to the nearer galaxies with some accuracy. Assuming the galaxies were, on the average, about the same size, he measured the distance to farther galaxies by looking at their sizes. When he charted the distance versus the velocity, he found that the farther away a galaxy was from us, the faster it was moving. That's the line sloping up and to the right. It was as if the entire universe was expanding. The slope of the line, the Hubble constant, tells you the speed of expansion. It's like baking a raisin bread. The dough starts small. Let's say that we are in the middle of the loaf, the blue dot. We don't have to be in the middle. This works no matter where we locate ourselves. We can mark a few raisins around us, some close, some far, and measure their distances. We bake the bread, and it doubles in size. The loaf is twice as large, and all the raisins are twice as far as they were before baking. Let's add the original distances. Every arrow has grown to double the size. Can you see that the farther raisins had to move much faster to cover the increased distance than the closer raisins? This is what Hubble saw with galaxies. So Hubble made the observation that the universe was expanding. How do we fit that idea into a theory of the history and future of the universe, something called a cosmology? A couple of camps arose, the steady-state theory and the Big Bang theory. The steady-state theory was one of the first hypotheses. It stated that although the universe is expanding, it nevertheless does not change its appearance over time. This is called the perfect cosmological principle. The universe has no beginning and no end. I personally find this theory very aesthetic. You don't have to worry about where the universe came from. It's always been there. Nor do you have to concern yourself about its eventual fate. It'll always be there. In 1928, Sir James Jeans was the first to propose a steady-state cosmology. Here's the problem. If the universe looks the same throughout its history, and yet it's also expanding, to keep looking the same, you have to create new matter from nothing. This new matter eventually forms stars, and the stars form galaxies, and the universe continues to expand and look like it always had, with the same density of stars and galaxies. No beginning, no end. In 1948, Bondi, Hoyle, and Gold refined Sir James Jeans' idea into a more rigorous steady-state theory, which holds, as I've stated, that the universe is constantly expanding, but matter is constantly created to form new stars and galaxies to maintain a constant average density in the universe. Georges Lemaitre published a paper in 1927 with the very long title, quote, "A homogeneous universe of constant mass and growing radius accounting for the radial velocity of extragalactic nebulae," unquote. In this report, he presented his new idea that the universe is expanding, which he derived from Einstein's general relativity. This later became known as Hubble's Law and is now known as the Hubble-Lemaitre Law. 4 years before Lemaitre's paper, Hubble discovered, using the spectra of galaxies, that it appeared the universe was expanding. Hubble was reluctant to accept this idea. Because of errors in his measurements, it looked like the universe was only 2 billion years old. Evidence for the geologic age of the Earth seemed to contradict this. However, once the issues with Hubble's calculations were addressed, the universe became sufficiently old. However, in a universe that was expanding and not creating matter between the galaxies, it appeared that when you ran time backward, there came a point when all the matter in the universe was crunched together. It looked like the universe was created at some definite time in the past. Fred Hoyle, proponent of the steady-state theory, laughingly called this the Big Bang theory, and much to his chagrin, the name stuck. The Big Bang theory states that around 13.8 billion years ago, for reasons we don't yet understand, the universe came into being, creating time, space, and matter. After about 375,000 years, the universe cooled enough for atoms to form, and after another 400 million years or so, the first stars formed, then galaxies, galaxy clusters, and the universe became as we now know it. Light from distant galaxies, traveling at 186,000 miles per second, takes longer to get to us the farther out the galaxy. So, we're looking back further in time when we look at galaxies that are farther away in space. Here, we're seeing thousands of galaxies in a very long exposure taken by the Hubble Space Telescope. This one frame contains about 10,000 galaxies. Hubble, the astronomer, could not have imagined a scene like this. By the way, this photo is actually a very small piece of the sky, only 1/10 the size of the full moon. One of the first problems for the steady-state theory came up when we were able to detect and measure very distant objects in the universe. We could see galaxies out to about 6 or 7 billion light years, here, marked in yellow. Beyond the galaxies were extremely bright and small objects called quasars, or quasi-stellar objects. We now believe that quasars are galaxies with extremely active cores powered by massive black holes. Those are shown here in red. The problems? Well, as you can see, the universe isn't the same throughout its history. Now we see galaxies and galaxy clusters, but we only see quasars when we look out further in space and time. And eventually, if we look out far enough, even the quasars disappeared before about 12 billion years ago. It looks like the universe has evolved. not what you'd expect from an unchanging universe. The next problem involves that mottled, colored strip you see on the right side of the diagram, 13.8 billion light years out and 13.8 billion years ago. If we look out far enough, we look back in time to only 375,000 years after the Big Bang. This is the time when the universe, because of its expansion, had cooled enough for neutral atoms to form. Before this time, the universe was a white-hot, opaque plasma. We cannot see beyond or before this plasma wall. As the universe continued to expand, this plasma continued to cool until today, when it is no longer glowing in visible light. This leads us to the last part of our story. Some time ago, our televisions looked like this, and we received our information through radio waves with a rabbit ear antenna on top of the set. When you tuned to an unused channel or frequency, you'd see and hear noise. Part of this radio noise was coming from the universe itself. It took a somewhat larger antenna to scientifically investigate this noise. Which brings us to a very special, sensitive, horn-shaped antenna in Holmdel, New Jersey. In the early 1960s, Bell Telephone Laboratories built this antenna to aid them with their research into satellite communication. It was used to capture extremely weak radio reflections from the Echo balloon satellites in low Earth orbit. In 1964, a pair of astronomers, Arno Penzias and Robert Wilson, seen here, started using the ultra-sensitive antenna to look at astronomical sources of microwaves. Oddly, they saw microwave noise coming from every part of the sky, north and south, day and night, summer and winter. Thinking they had a problem with the telescope, they troubleshot all their instrumentation and the telescope itself, even removing nesting pigeons and their droppings from inside the horn, all to no avail. This noise was 100 times more intense than they could account for. It was as if the entire universe was heated to a temperature of 3.5 degrees above absolute zero. Penzias and Wilson were in need of an explanation for these microwaves. Luckily, a physicist friend of Penzias, Bernard Burke, told him of a preprint paper by 3 astrophysicists at Princeton. Robert Dicke, Jim Peebles, and David Wilkinson reasoned that if the Big Bang had occurred, that there should be some leftover radiation from the event, but now cooled down from the white-hot plasma to something giving off only microwaves. They were about to embark on experiments to find this cosmic microwave background. Meanwhile, Penzias and Wilson, upon reading the Princeton paper, realized the significance of their measurements. What they had seen in their horn antenna matched perfectly with what Dicke, Peebles, and Wilkinson had predicted. The cosmic microwave background was there, was real, and evidence for the Big Bang was solid. Penzias and Wilson received the Nobel Prize in Physics in 1978, and Peebles in 2019 for their contributions to the field of cosmology. These measurements were not the last word, however. The 1964 measurement by Penzias and Wilson with the Bell Labs horn antenna was very low resolution and really only gave a single temperature for the entire universe, 3.5 degrees above absolute zero. No detail at all, only the fact that the universe was still glowing with microwave radiation. From 1989 to 1993, the COBE, or Cosmic Background Explorer satellite, mapped the microwave radiation from the Big Bang in a bit more detail. Structure of the early universe was becoming a bit clearer. From 2001 to 2010, The Wilkinson Microwave Anisotropy Probe, or WMAP, named after David Wilkinson, provided even more detail of the structure of the early universe. Things were becoming a bit clearer. And most currently, from 2010 to 2013, the Planck satellite has given us our highest resolution view of the early universe as it was only 375,000 years after the Big Bang. The temperature variations seen in these maps is very small, only 2/10,000ths of a degree between dark blue and bright red. But this is an indicator of the forces that set up the universe to form its vast webs of galaxies and superclusters, making the universe we see today 13.8 billion years after the Big Bang. The detection of the cosmic microwave background sealed the deal for the Big Bang theory. The steady-state theory could not account for the microwave background or the structures we see here. According to Stephen Hawking, the cosmic microwave background was the final nail in the coffin of the steady-state theory. Thank you for viewing Full Spectrum Science Shorts, presented by the Exploratorium in San Francisco. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.